Welcome to lesson number 3 on potential energy diagrams. Our lesson objectives: determine if a reaction is endo or exothermic based upon the potential energy of the products and reactants, label all the parts of the potential energy diagram, calculate the heat of a reaction, and finally draw a catalyst on a potential energy diagram and describe how it affects the reaction. A potential energy diagram is a way to show the change in potential or stored energy during a chemical reaction, and it looks much like this. And so we can track that change in energy from the reactants to the final products. And so let's look at the two different types of potential energy diagrams. The first one being exothermic. So an exothermic potential energy diagram has the products much lower than the reactants. So the product side is lower than the reactant side because in exothermic reactions, the energy is being released or produced, so the net amount of potential energy is going to decrease. We're left with less energy than what we started from. And so that delta H is negative because delta H is the products minus the reactants. So in terms of potential energy, we have products minus reactants, we end up with a negative value. Endothermic is the opposite. In an endothermic reaction, we are absorbing energy, taking energy in. And so we're going to end up with more energy than what we started. So the products have more energy than the reactants. And if you do the energy of the products minus the reactants, you'll get a positive delta H. Let's check your understanding. Can you determine if a reaction is endothermic or exothermic based upon the potential energy of the products and reactants? Now we're going to go through the potential energy diagram and label all the parts. And label these in your notes. So in your notes, you're going to have blank potential energy diagrams, one for endo and one for exothermic. And so as we go through each part, make sure you label it in your notes. The first part is the activation energy, or energy of activation. This is the minimum amount of energy that's required for a reaction to occur. So if you think of the diagram here, these bump diagrams, it's the energy needed to get over this hill, the initial hill. So I put some numbers here just so it makes it easier to understand what's going on. So we start out in a reaction at the reactants. So the reactants already have energy. In this case, we're starting out at 50 kilojoules. And so the activation energy to get this reaction going is the energy to get over this hill. And so this is my activation energy here. And so in terms of potential energy, we have 200, we have 50, so the activation energy is 150. That's how much energy is required to get this reaction to go. If we don't have 150 kilojoules of energy being added to our reactants, then we're not going to reach the top of the hill. We don't have enough activation energy and the reaction won't take place. For the exothermic reaction, here is our activation energy here. So again, starting out the reactants, and we're adding, in this case, 50 kilojoules of energy to get the reaction to take place. Notice that the exothermic reaction doesn't require as much energy as the endothermic reaction to get the reaction going, and that's why exothermic reactions are typically spontaneous. The next thing I'm going to label is the activated complex. This is the highest point of our potential energy diagrams. It's a temporary state, and it's where bonds that are broken and are starting to reform. So if our reactants are being broken apart, that's going to take place here once the activation energy has been met, and then they start to reform to form our products. So the activation energy goes all the way from 0 up to the top. So it's how much energy does it take at the highest point. So in this case, it takes 200 kilojoules of energy. That's the highest amount of energy in the reaction. And for exothermic, it's the same thing here, going from 0 all the way to the top of the hill. The heat of the reactants or products, we say heat of reactants or products, but really it's the potential energy of the reactants or products. How much energy do they have? So it's the amount of potential energy possessed by the reactants and the products. So let's first look at the reactants here. So how much energy do they possess in the beginning? The reactants possess, in this case, 50 kilojoules of energy. So it's the amount from 0 to the reactant line. That's the potential energy that the reactants have. How much energy does the products have? 0 to approximately 150. So they have 150 kilojoules of energy. Since this is endothermic, that makes sense because we're adding energy to the reactants, so the products are going to have more energy than the reactants that we started with. For exothermic, so here is the energy of our reactants. In this case, they have 150 kilojoules of energy. Exothermic, it's going to give off energy. That's why you see the energy potential energy diagram decrease. And our products have a lot less energy. In this case, they have 50 kilojoules. Let's check your understanding. Can you label all the parts of the potential energy diagram thus far? Now let's look at the heat of reaction, the delta H. And we've covered this before on table I, our delta H values for certain reactions. This is the amount of energy that's lost or gained in a reaction. So it's tracking the difference or the change in energy. And so it's the energy of the products minus the reactants. So if we look at the endothermic potential energy diagram, the energy of the products here is 150, and the energy of the reactants is 50. So this difference, this change, is our delta H right here. And so products are 150 minus reactants here, which are 50. So this is a positive 100 for my delta H. So in this case, since it's endothermic, we've added energy, so we added 100 kilojoules of energy. Exothermic, it's still products minus reactants, so it's still the same change. The number's still the same, but now products are 50, reactants are 150, so 50 minus 150 is negative 100. So that's why when we switch or reverse a reaction, the sign switches. The delta H, the change in energy, is still the same. And so on table I, if you look at an example like this where we are synthesizing water, it's a negative delta H, meaning exothermic, which the graph is going to look like this here. And then if we reverse the reaction where we decompose water, we're going the opposite direction, as in the case here, that's why we switch the sign. So if for endothermic, now it's products minus reactants, we end up with a positive value, and that's why it's a positive 571.6. Let's check your understanding. Can you calculate the heat of reaction? What happens when we add a catalyst to our potential energy diagrams? Well, remember, catalysts lower the activation energy. The energy needed to start the reaction. They make it less, and therefore the reaction occurs more often and much faster. And so you're often asked to draw in the effect of a catalyst. So the catalyst is going to start at the same place. It's not going to change the energy of the reactants. And it's going to get us to the products faster, but we're still going to have the same amount of energy in our products. And so the catalyst would look something like this. So we're starting the same. All it's doing is it's lowering the activation energy, the energy required to start the reaction. What it does is it gives us an alternative pathway to get to our products. And so you notice here that the activation energy is much less than the initial activation energy going all the way to the top. And the same thing for exothermic. We're going to start the reactant, same place, much lower bump, so much lower activation energy, and it gets to our products, so we're ending in the same place. So again, a decrease in activation energy makes the reaction happen faster. Let's check your understanding. Can you draw a catalyst on a potential energy diagram and describe how it affects the reaction? At this point, you should be able to determine if a reaction is endo or exothermic based upon the potential energy of the products and reactants. Label all the parts of a potential energy diagram, calculate the delta H, or the heat of reaction, and draw a catalyst on your potential energy diagram and describe how it affects the reaction.